boop. Boop 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 boop.
Boop, 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 boop,
Boop boop.
boop. Hi, everyone. As always, this is Joel,
And this is Brittany.
and welcome to the Periodic Roundtable again. Brittany, what will we be talking about today?
So today we'll be talking about Earth-like planets, what they are, how astronomers detect a planet that it's Earth-like, what qualifications must be met for a planet to be considered Earth-like, and we'll also be discussing the possibility of humans reaching these planets. But at what cost will we become the new plague on not only our current Earth, but planets throughout the galaxy as well?
But Brittany, we must acquire more resources.
We always need to acquire more resources, but at what cost?
Whether we are transversing the Atlantic Ocean, the ocean of people, or the ocean of dark, cold space,
Yeah.
we will find more resources.
Yeah,
Specifically water.
water.
Water is a valuable resource.
Water is a very valuable resource. In fact, it's one of the most important resources in order for a planet to be considered Earth-like and can support life.
Okay, so let's get into what causes the planets to be Earth-like. What are the defining characteristics that we would want to look for?
Right, so first we can describe it as a planet that has the same mass of Earth. So Earth has a mass of 5.972 times 10 to the 24th kilograms. But this planet might not necessarily be inhabitable or even have an atmosphere.
So then why are we worried about the weight? What does it matter how big and girthy my planet is?
Exactly. So there's a few more markers that will define what an Earth-like planet is. One of these is the fact that the planet is terrestrial. So a terrestrial planet is a planet composed of silicate rocks and metals, and it has a solid surface. So think of our gas giants. Those aren't considered terrestrial planets. They're not rocky. Our inner planets, however, in our solar system count as terrestrial planets.
Because we can walk on a firm, hard ground?
Yes, but
And-
you can't do that with a gas giant, obviously, because it's gas.
What if we condense the gas first and then we're walking on clouds? Have you ever walked on clouds, Brittany?
I haven't.
Well, I was there recently.
Yeah.
Anyways, as we look forward, what are other ways that we can focus on the descriptions of Earth-like planets?
Okay, so if we want to get really specific as to what an Earth-like planet is, we turn to what's known as an Earth analog. So an Earth analog is a planet or even a moon, in some cases, that has a similar surface to Earth, both environmental and by the atmosphere. So this episode actually will focus primarily on Earth analogs.
Okay, Earth analogs. Mm-hmm. And how do we get to an Earth analog? Is it like a twin of the Earth? Something that is birthed long ago that we need to find, almost like a lost cousin out at sea, stolen by pirates, that we're sailing through the glorious flood spreading across the galaxy?
Yeah, kind of. It can be a different mass, it can have different seasons and temperatures, but primarily an Earth analog is a long-lost cousin of Earth.
So there might be, say, a Gaia world, or a more paradise-style world that might have beautiful, phenomenal weather all year round.
Yeah, and it can also be a world that is a Arctic nightmare. It could be a world that's way too hot, but just enough so, we're not dying or anything. There's a lot of extremes that you can go to when it comes to Earth analogs.
I'll take my paradise one. You can take the Arctic nightmare.
Fair enough.
Perfect.
All right.
But let's get into more these, what do you say, continuous habitable zones?
So yes, the planet must be in a star's continuous habitable zone, or CHZ. And what this is the region of a star in which the planet remains habitable over a long geological time period. So this time period must be at least that of Earth, which is 4.54 billion years. And this allows for a habitable biosphere to form.
So 4.5 billion years in order for some biosphere to form, right?
Right.
Is that a long time? Have we rapidly grown as a divergent species collection on this rock flying through space?
So as far as humans go, we actually haven't been on this planet that long, about 1 million-ish years, give or take. But life has been on the planet for far, far longer. It's just that this time period is required to have a biosphere to allow us to live on it as well, because that's the ultimate goal.
4.5 billion years. Okay. Now I'm imagining, say we think of a jungle, such as the Amazon, where it's raining, it's hot, it's humid. You have the capabilities of all these plants growing to massive, insane sizes. That where your vines are as big as legs, your trees are massive and overgrown, these beautiful canopies, right?
Right.
And then we go look at the Arctic, where there's very small little wintergreens popping up just a few inches off of the ground covered in snow, and you have hardy, girthy animals that are scarce and far between because of the lack of resources, right?
Right.
So 4.5 billion years, I would imagine, can be changed depending on the environment that you have developing the biosphere.
Right. It depends on what kind of atmosphere, what kind of temperature you have. So there are a lot of different requirements for life, but life doesn't have to be life that we see on Earth. So it can kind of give or take the 4.5 billion years for this continuous habitable zone, for a planet to be in the continuous habitable zone for this long.
So if we found an ocean world where there's only a few tiny islands, and there's scarce little primate-style creatures lurking in fear as the massive, true masters of the world
Yeah.
swim about.
Yeah, pretty much.
Okay.
Yeah.
But if we want to look at Earth-like analogs specifically for humans to inhabit, I imagine that they do have to be terrestrial.
They do have to be terrestrial. So, of course, we can't really have life on a gas planet as far as we know. But especially for humans to live on, we can't live on something like that. So, yes, the planet has to be terrestrial. In addition, it has to have a surface temperature that allows for liquid water to occur, because water is a very important building block for life.
So in between 100 and 0 degrees Celsius.
Yes. It can actually be a little bit lower, a little bit higher, because the water can be frozen, but you can still use that water. It can also be condensed. So as long as it's a surface temperature that is pretty close to this range, and we can have the liquid water, that is something that we're looking at.
Sweet, sweet resources.
Sweet resources.
The most valuable resource.
The most valuable resource, and we're back to the beginning.
Back to the beginning.
Yes.
Well, we're not done making circles. Let's talk more about circles, though.
Indeed. So another thing that this planet has to have is a circular orbit. This allows for constant conditions throughout the year with small variations such as seasons.
So because of a circular orbit going around some star
Right.
far off, and the star doesn't even know that you're there,
Yeah.
are we just leeching off of it,
Yeah, pretty much.
taking its sweet, sweet energy?
Yeah, it's sweet photons.
Sweet photons. Just like you have a happy, bubbly person running about with the energy of 1,000 puppies, and you're just standing around absorbing, leeching off the energy.
Yeah.
Okay.
Transferable energy.
Transferable
Yes.
energy. That would help making the biosphere over the X amount of billions of years for this planet.
Right, because it'll have constant conditions. So you think of a planet that has a more ellipsoid orbit, it's going to have a huge variation in temperature. So it goes really far away from the star, it gets really, really cold, then it gets really close to the star, it gets really, really hot. So you can't have a continuous biosphere forming because of a ellipsoid orbit. So close enough to a circular orbit. Ours is more of a squished circle, but close enough.
Smaller variations. But you're saying going around one sun, right? Let's
Right.
talk more about stars nearby planets and how they will affect it.
Right. So this planet that is, going to be our theoretical planet that we're looking for to transfer to, it also can't be too close to a supernova or a massive planet because this can affect the smaller planet's orbit. So it can throw it out of the circular orbit and therefore destroy the biosphere that was forming.
So we can't have a large planet near us, and we can't have supernovas.
Right.
What if the supernova takes a long time and you're staring at it with these massive, thick sunglasses? Whoa, man.
Well, as long as it doesn't affect the gravity of the orbit, then it should be fine.
So that's what we need, is the gravity.
Yes.
The enemy that's holding us down,
Yeah.
man.
It's holding us down. Gravity's just the biggest man of all.
Gravity we need for our organs, right? That's one of the difficulties that we have for space travel specifically, is that your organs start shutting down over a period of time because it doesn't have gravity.
Right.
Okay,
Yeah.
that makes sense. And the destruction of our muscles, because your body is like, oh, you no longer need these anymore.
Yeah,
I'm going
so-
to take them away.
Yeah, so that's a common problem with astronauts on the ISS, the International Space Station. Their muscles will atrophy over time, so when they get back, they lose a lot of muscle tone. They're very weak. It's hard for them to walk. It's just a side effect of being an astronaut, unfortunately.
Okay, we need gravity in order to survive. We talked about water. So water is important. Why?
So water is important because it acts as a solvent for complex chemistry to occur, and it also helps regulate the thermal balance thanks to its high heat capacity. So heat capacity is energy required to raise the temperature by 1 unit. This allows us to keep a constant thermal temperature range for our body.
Okay, which has a relatively low heat capacity or high heat capacity?
It has
for
a
water?
high heat capacity. Water.
I see. So
Yeah.
it can contain a lot of heat, and it requires a lot of energy in order to heat up, which allows for a regulation of temperature.
Right.
Which is why the ocean never gets too warm when you're next to it, and why coastal cities are the best.
Yes, that's true. Also, if we are outside for long periods of time, we don't get overheated really, really quickly. So think of, you're outside on a hot day and you touch something metal, then that heats up really, really quick. You don't want our body to do that if we're outside for long periods of time. Same with cold temperatures. We don't want our body temperature to just suddenly plummet.
Water, which is the majority of our body, keeps us alive as long as it's not heated too fast or too slow.
Right.
Well, what if we were to zoom down further in? What really makes us us, Brittany?
That is the question that we all ask all the time.
That's not the question we're answering in this podcast. What I was actually talking about is the more cellular biological aspects of our body. The RNA, the DNA, the nice amino acids, the proteins building up my strong, rippling muscles.
Right, so you need ambient temperatures about 15 to 115 degrees Celsius on this planet in order for these things to actually be viable. So for example, at really low temperatures, you're going to have lack of liquid water. As we talked about before, you'll have ice. And then at high temperatures, that's when you get into the biocomplexity of it. So proteins, carbohydrates, RNAs, and DNA will start to break down at 125 degrees C. So you don't want to get too close to this temperature.
At 115, I will start breaking down.
We're kind of in the middle of a bit of a heat wave right now, and I'm feeling it.
For these RNAs, DNAs, and everything else that we need in order to create a cell, these biospheres, which I would like to do a episode on the origins of life, or at least what evolutionary biologists believe occurred for us to form the way that we have. One of the ways that we can look at it is phospholipid bilayers. If you take the micelles, or if you take phospholipids, throw them into a little bucket of water, they will, without energy input, create little micelles. So you now have little capsules holding everything together on the inside, right? So we have that aspect. And if we have too much heat, obviously you'll form less micelles because they'll break apart faster.
Right.
So at a certain temperature, which will be important for the development of the biosphere of this Earth analog, will be paramount for us to invade and infiltrate the already developed RNA and DNA that would be there.
Right.
Unless there's something else that's not RNA and DNA that they've developed.
Yeah, questions, because we don't know. We haven't really found any other types of life outside of what we know in bacteria. So
instead of carbon-based, what if it was, say, sulfur-based?
Sulfur-based, that would be interesting. There are some theories of silicon-based life.
Silicon-based life.
Yeah.
So glassy, powerful shard creatures.
Yeah, that's kind of scary to think about, but yeah, it could happen.
I'm imagining a glass panda bear flombling around, and you can see through it, and you can see your own soul inside of its nice, still beating silica pump.
Yeah. A glass panda bear.
Panda bear.
I think that would make them even less likely to survive. They're already having some issues. You don't want to convert it to glass.
Even if they are having a hard time, Brittany, if they're glass, perhaps they can make their own photovoltaics. But for photovoltaics, you're developing energy, right? So no matter whatever type of life you have to have some input of energy, right?
Right. So this energy can be either light or chemical energy because you need to promote chemical reactions. So sunlight's not the only energy source. You can also have extremophile microbes that thrive near thermal vents deep beneath the ocean surface. And bacteria can survive in polar ice or deep underground because they're relying more on the chemical reactions instead of the light reactions.
So give me chemicals or give me light.
Yes, that was what the original saying was, believe it or not.
Right,
Yeah.
give me chemicals, give me light.
Uh-huh.
And then somehow...
It got translated to give me liberty or give me death.
But liberty, in a way, is just the right chemicals.
Exactly, yeah. Everything's chemicals.
Everything.
Yeah, I'm chemicals, you're chemicals. We're all chemicals.
If we're all chemicals, and we're all oscillating at a particular frequency inside of this universe, perhaps there's just one collective unit of a molecule that we're inside of, right? So just like the orbits of electrons around nuclei as an atom, our planet is rotating around the sun in the same way, in a relatively predictable manner, with a certain spin, mind you, just like an electron. So together we're forming one
Whoa.
atom together.
That's deep, man.
Well, let's get less deep. So, we talked about energy, but what about nutrition?
So we have to have nutrition, of course, in order for life to occur. You can't go without eating. Nothing really can go without having some kind of nutrients. So a water cycle or volcanic activity is important to replenish nutrients. And in addition, we also need an atmosphere comparable to Earth's. So Earth's atmosphere is 480 kilometers thick, and this protects us from UV radiation. So alternatively, life can develop underground or underwater away from these harmful UV rays, but it's really helpful to have an atmosphere that will protect life on the surface from this UV radiation.
So a nice woolly blanket of something keeping away all the radiation, destroying us.
Right.
What about the UV rays? Why is it so harmful, Brittany? Why is the penetration inside of our bodies of these unforeseen rays?
So UV rays are really high energy, and most people are aware of UV rays being blocked by something like sunscreen. So the high energy rays can actually cause mutations, and that can lead to cancer. It's hard for life to develop with these really high energy rays.
It's true. And some life is even more sensitive. So for example, on the surface of water, if you go down a few centimeters, there's an entirely new biosphere of microbes and activity just because of the amount of light that's coming in. Because you have a trade-off about how much light you're blocking as to how much radiation poisoning each microbe gets, but you then decrease the amount of energy that you can produce because of the lack of photons.
Yeah, so it's kind of a bit of a trade-off there.
So we have to consider what type of radiation is going through, and if we need to just toughen up and get rid of our mutations, or accept them as one, or grow a third arm.
Yeah, either way. Some mutations are beneficial. Most of the mutations that you get from lots of UV rays aren't.
I mean, mutations is how we got here to begin with.
Yeah, exactly. That's what evolution is.
That's after 99.9% of mutations were killed off.
Yeah, pretty much.
If I recall from modern physics before, is that as stars start developing and heating up, you have a whole bunch of hydrogen and helium collapsing together and fusing, creating a massive release of energy, right?
Right.
And then eventually this heat gets high enough to where helium can combine, and you start having a development of a whole bunch of elements because you're combining different nuclei, therefore increasing the mass of each element, and that will in turn change it, right?
Right. In a process known as fission.
And so you have a naturally occurring abundance of elements depending on the stars that are nearby and how they have shot off whatever piece of it is, and you have them floating through space, right?
Right.
Now, what would we need as far as elements for an Earth analog to have a biosphere that could potentially be inhabitable?
So we need elements present that are heavier than hydrogen or helium, preferably carbon or silicon, so we can get those building blocks for life. But we also need other types of elements too. For example, we need phosphorus, we need nitrogen, we need oxygen. We need these heavier elements in order to develop life, because life is dependent on things that are outside of just what is in a star.
We need water, we need certain temperature, we need atmosphere, energy, nutrition, elements, all combined together.
Yes.
Right? That's a lot of things to look for, Brittany.
Yeah.
How in this world, do we find other worlds that have all of these aspects? Because that's a lot of information to gather from millions of light years away from us.
Yeah, there is a lot of requirements, and so it can be kind of hard to find a planet that meets all these requirements. But astronomers have a lot of methods to detect planets, and we'll actually go over a few that are pertinent to what kind of Earth-like planets we're looking at.
Okay, that's exciting.
Yeah, it is. It's very exciting. I love these methods. They're really cool. So there are many, many, many methods, but there are 3 that I chose for this particular topic because these are the ones that are most used, and the most used for Earth-like planets in particular. So the first one I wanted to talk about was something called the transit method. So what they do is they will use a telescope such as the Kepler Space Telescope, and an astronomer can detect when a celestial body passes in front of a star. So think of an eclipse, and the amount of light that is dimmed reaching the telescope can infer information about the planet's size.
The amount of light that is dimmed because it's moving about and it's blocking whatever it is.
Right.
How big is the silhouette
Exactly.
of this
Yeah.
planet is what you're telling me.
Yes.
So we are playing shadow puppets with the planets far away in order to talk to them.
Yeah, exactly.
But one way. 'Cause
Yeah, one
they're
way. Yeah, it's not mutual.
Not, it's not mutual.
No.
They don't care.
Yeah, very
They
sad.
never listen.
Yeah.
Just like you. You never listen.
Listen all the time.
Okay, that's one size, but we talked that size isn't necessarily a component. It doesn't matter how girthy my planet is. There are other important aspects. How do we get further? How do we get more information?
All right, so we also want to know what the actual mass of the planet is. Size and mass aren't the same thing, even though a lot of people might think it is. And we also want to know how far away the planet is from the star, so we rely on a few other methods. We rely on other methods too because up to 35% of planets detected using the transit method are believed to be false positives from space dust or debris because other things can also pass in front of stars instead of planets. So we need to be able to use other methods in combination with the transit method in order to not only get rid of these false positives but find more information about the planet itself. So another method is known as the radial velocity method.
Okay. I'm excited. I just want to point out one thing though. You said space dust or debris.
Right.
So trash. Debris is trash, right?
Yeah.
So as we're looking for a succulent, beautiful, curvy planet in order to fertilize with our DNA,
Oh my god.
you're telling me that trash gets in the way.
Yes.
And keeps us from trying to find a true succulent planet.
Yes.
All right, I just want to make sure. That's what you said.
Okay.
Precisely.
Yeah, that's what I said.
Radial velocity method, though.
Yes. Yeah, radial velocity method. So this is another method that astronomers use to get some more information about these planets. So what they do is look at something called the Doppler effect. The Doppler effect is when a wave changes frequency as the source and the observer move away or towards one another. So the way they do this and why they do this is they're looking at the minute wobble a star has on an orbiting planet. A planet will actually pull a little bit on the star. Everything pulls on each other. So of course the planet is being more pulled by the star, but the star is also being pulled by the planet. So astronomers will use what's known as Doppler spectroscopy to determine changes in the radial velocity of the star, or the speed that a planet will go around the star. And that way they can use the radius of the planet calculated from the transit method and the degree of movement from the star. They can determine the density and the composition of the planet.
Wow.
Yeah.
So the Doppler effect, just like I'm standing on a street and I hear sirens of an ambulance go by and the pitch changes as it passes me and keeps going.
Right.
We're using that exact same method of where we're getting some particular frequency based on the planet's movement.
Yes.
And from that, we can look at the wobble.
Yes.
Wobble, baby. Wobble. And from there, we can see, you said the density and composition? Composition.
Yes. So whether it's a terrestrial planet or a gas-like planet.
How is it that using this Doppler effect, we can see the composition?
So that is a lot of complicated math that I will not get into. But they are able to find the change of frequency of the wobble from the Doppler effect. Another example of the Doppler effect, if you're not familiar with it, is you might hear on TV stations when the weather comes on and be like, new Doppler effect news, and it'll tell you about what kinds of weather is coming, and they use the Doppler effect as well to determine what future weather patterns will be.
So now we have the transient method and the radial velocity method, and we've understood the mass, the size, composition, and density. But there has to be more in order to actually understand all the information that we want.
Exactly. There are a lot of methods that astronomers use to detect planets. I'm only going to get into one more though, and I'm going to talk about this one because I thought it was super cool. So it's called the Gravitational Lensing method. And how this works is really complex, but I'll try my best to break it down a little bit. So what happens is that two stars will line up, and the foreground star's gravitational pull will actually act as a lens to magnify light of the background star. So if the foreground star has a planet, that planet's own gravity will detectably increase the lensing effect. So the lensing effect will cause it to get brighter. And we can already see this when a star is passing in front of another star. We can record what kind of lensing effect is there, but if it has a planet, it'll be an ever so slight change. Yes. So it's most effective when a planet is between Earth and the center of the galaxy, because the center of the galaxy has a much higher amount of possible background stars.
Okay, so if we have that alignment, then we can actually see this small increase because of this gravitational lensing, right?
Right.
But how do we confirm that these aren't false positives? So for the transient method, you said we have 35% that's false positives.
Mm-hmm.
Now, what about the gravitational lensing? Is it more reliable?
Yeah, it's actually way more reliable than any of the other methods, but the downside of it is that it usually can't be repeated because the chance of the same alignment happening again is really minute. So you think about all these things that are constantly moving. The chance of getting that same alignment and getting another data point is really, really minute. So it's a lot more reliable than these other methods. It just can only be used once. And in addition, it can only be used to determine the mass of the planet and not its composition.
I see. Okay, so we're getting some weights back in here.
Yeah.
That is a really cool method, though.
Yeah, it's really cool. It's
Gravitational
very
lensing.
complex, but very, very cool.
Okay.
Yeah.
And you said there's a few other methods, but we won't be getting into them.
Right. There's a few other methods that we can use to determine what exoplanets are and if they're there, but they're not reliable for Earth-like planets because they tend to require the exoplanet to be really massive and far away enough from a star or to be orbiting a dim star, such as a brown dwarf.
I see. Okay, so we have what we want.
Mm-hmm.
We have how to find what we want.
Right.
Okay, so now we're looking through a telescope, our little scopy thing, looking at the sweet succulent planet that we've picked out. We're sitting in this galactic bar, and we're all having nice drinks of water, delicious water. And we finally see one. We see one far away, off in the distance.
Between the crowd.
Between the crowd.
These
One,
other
they
planets.
brighten up because of the
Yeah.
gravitational lensing,
Yeah.
just a little bit.
Yeah,
So
just
we
right
know that
there.
they're there.
Yeah.
How do we get there? How do we go find? How do we approach this
we
planet,
approach?
you
All
know,
right.
and buy them a drink
All
of
right.
water?
Yes.
Yes.
So, yeah, we want to talk about if it's ever possible to travel to these planets. What we can look at is the Earth-like planets that we've already discovered so far.
Okay.
So we can talk about, for example, the closest one to Earth, which is known as Proxima Centauri b. And this was a planet that was found to be in the habitable zone of a red dwarf called Proxima Centauri. It was found using the radial velocity method that we earlier talked about.
That's cool.
Yeah, and it's believed to be about 127% the mass of the Earth, and it has an equilibrium temperature of negative 39 degrees C. And
Now, hold on. That sounds pretty cool.
it's pretty cold, but we can actually survive at these temperatures. It's, it's not pleasant, but we can always, build these little biodomes and live a nice, happy life inside them.
Inside of a biodome. All right. I'll live inside of a biodome if it can keep me warm.
Uh-huh.
But I want to know, right? We
Uh-huh.
talked that I hate sleeping.
Right.
So what are the days like? Will I have better days here?
You might, because a year there only lasts 11.186 Earth days. So 11 days for 1 year. You can get so little sleep in 1 year.
In
there.
1 year?
Yeah.
Wow.
Yeah.
Okay. But what will that do to my body? Will I age faster? Will I age slower? Will I be a wise elder before my time?
I mean, you could be, since a year is only 11 days, and I imagine we would probably age about the same rate. So you can say, oh yeah, I'm hundreds of years old.
Well, aging will be related to the amount of gravity that's put on you, because
Yeah.
that's going to change the
Exactly.
temporal space
Yeah.
activities of your body.
Exactly. So have a little bit different gravity too, because the mass is slightly different from Earth, 127%. So the gravity will be a little bit higher.
So we'll age faster.
Yeah.
But every 11 days we can party.
Exactly.
Okay. How far away is this, and how do I get there?
Yeah, so it's actually not that far away in the grand scheme of things. So it's 4.2 light years away, and this is also 3.97 times 10 to the 13th kilometers.
That's really far away.
Yeah, for us, but in space terms, it's pretty close. Very close.
So not that far. So if we
Yeah.
could find some way in order to travel near the speed of light
Yes.
for more than 4 years,
Yes.
we could get there.
Yeah, so right now we don't have these means. So far, the fastest spacecraft record that we've reached was reached by the Parker Space Probe, and this was going about 300,000 kilometers per hour. So we can use this as a frame of reference, and if we were able to go that fast, it would take 115 million hours or 13,206 Earth years to reach this planet at these speeds.
Okay, so let's say we perfect medicine appropriately so that you live exactly 100 years, right? And then every time your generation gets to year 90, they have a child,
Okay.
right? That's 100 years. How many? That's a
That's
a lot of generations.
That's a lot of generations.
To live on a spacecraft.
Yeah.
And then your grandparents are always telling you stories about the ancient days.
Yeah.
Back at the home planet before it was destroyed and we were sent off. And now your entire life is developed just to go to this one place that you might never see.
You probably will never see.
Wow.
You're just that next step to get some more people to the planet, people that don't even exist yet.
14 generations. Can you imagine being 14 generations in, where the past 13,000 years is nothing but your ancestors telling you that you have a mission?
Yeah, pretty much. That would be awful. Would your life really have meaning at that point?
Does it have meaning now?
Does it?
I mean, we're doing this.
Yeah,
so.
yeah.
But if we were to go near light speed, that's going to be, like we said, about 4.2 light years, right?
Yeah.
Okay.
So 4.2 years.
So we just need to get faster.
Yes.
But
much faster.
I don't necessarily see that happening anytime soon. Are there other ways that we could look at other planets in order to inhabit besides this 4.2 light year away one?
Yeah, so instead of looking at these planets that are really far off, we can also turn to something called terraforming. So this is a hypothetical process in which a planet undergoes modification, either of its geological surface, its atmosphere, temperature, water levels, or ecosystem. And this is done to make it habitable to humans and other life as well.
So somehow, let's say we throw a big galactic party and we just throw water balloon after water balloon at one of these planets.
You would need a lot of water balloons.
A lot of water balloons,
yeah.
okay.
Mm-hmm. Yep.
Or we shoot nukes at them and we try to change their entire atmosphere.
You want to shoot nukes at the planet and then go live on it.
Listen, I'm not the first one to say this.
So this was a process that was initially proposed by Carl Sagan. Everybody knows Carl Sagan. He proposed this in 1961 concerning Venus, and this was a paper that was published in Science. And what he said was he could think about seeding the atmosphere with algae, and this would reduce the CO2 levels and subsequently drop the surface temperature.
So reducing CO2
Yeah.
as would help for
Yeah.
dropping certain temperatures.
Mm-hmm.
Okay,
Yeah.
okay. With algae.
Mm-hmm.
It sounds like a great idea.
It's a great idea, but there's one problem. So it was unknown at the time that the clouds of Venus were essentially concentrated sulfuric acid solution. And in addition, the atmosphere was incredibly thick, and they didn't know this at the time. So this results in a surface temperature of 450 degrees C.
Sulfuric acid? I mean, how bad can sulfuric acid be?
It's pretty bad. You do not want to breathe it or touch it. I mean, it's concentrated. Very concentrated.
Concentrated.
Yeah.
So sulfuric acid is actually something that they use in chemistry in order to create a certain solution called piranha.
Right. Piranha's great.
Which is exactly how it sounds, will eat away organic matter rapidly and viciously.
Oh, yeah.
Non-stop.
Mm-hmm.
So if you want to see what your bones look like, put a little drops of piranha on your body.
Yeah. The other half is hydrogen peroxide.
Why are you telling them how to make this, Brittany?
They might need to know someday.
We take no legal responsibility for what you do with hydrogen peroxide and sulfuric acid.
Oh yeah, it's not our fault. You know, if you want to burn your body away with piranha, go for it.
Do whatever you want.
Yeah.
Additionally,
so instead of looking at Venus, perhaps it's a little easier to look at other inner planets. For example, Mars. So Carl Sagan also went on to propose planetary engineering of Mars in 1971 in a journal known as Icarus. So terraforming Mars would be much, much easier, and it would require only two things. It would require the building of an atmosphere and the increasing of the thickness of the new atmosphere, so greenhouse gases such as CO2 can trap solar energy and increase the surface temperature, because the surface temperature of Mars is much colder.
I see. So we need it to be warmer, and we need more CO2.
Mm-hmm.
We take all the large oil corporations,
Right.
and we just ship them over to Mars.
Yeah, that would solve a lot of problems at once.
Okay.
Yeah.
Or we build a pipe, a big pipe,
Mm-hmm.
and we just exhaust all of our CO2 onto Mars.
Are you proposing a pipeline?
We... I suppose I am.
Yeah, all right. What happens if we get protesters, in between Earth and Mars on
Then-
this pipeline?
We'll just shove them until they fall into Mars' atmosphere, and they will start the colonies. They will be the true pioneers, as are all pioneers who
okay.
once protested against something and then
Genius.
was thrown off into the wilderness. Okay, so now we have the capabilities of potentially finding a planet
Right.
to live on, or terraforming something that's closer by.
Mm-hmm.
What happens if we destroy ourselves? What happens if we become the plague, if we're a virus spreading, just like Smith said in The Matrix?
Yeah, I mean, Honestly, we probably do have these capabilities if we don't destroy ourselves first. That's kind of the problem. The Earth is rapidly undergoing changes at alarming rates. Our CO2 emissions are extremely high. The polar ice caps are melting. We're undergoing mass extinctions. Are we even going to be able to make it to either of these ideas, terraforming or making it to a planet?
No. There's plenty of doomsday sayers that say we're not going to last that long. But if we were to look at the rapid changes of the biosphere, humans haven't been around that long.
Right.
And it's very possible we won't be around for much longer anyway.
Yes. Honestly, too, if we die off, our planet will be okay. It'll be fine in the end.
It'll be better off.
Yeah. It's just like, getting rid of an illness or something. It's like,
Right.
forces itself out, and then it's fine.
So, what you're saying is we're an infection on Earth.
Kind of, yeah.
But how, instead of being parasitic, how do we be more symbiotic in order to keep alive long enough to infect another planet? Or should we even infect another planet, Brittany?
Yeah, I mean, do we really want to be this plague that goes throughout the galaxy or even the universe, spreading and taking over a planet, and then destroying that planet too, and then going to the next planet, taking that over, destroying it? Do we really want that?
That's a massively moral question, and one that NASA has foregone by every time they have a space probe that they're sending far off into space. They will actually sanitize it so that no microbes are being sent into space for fear of starting another colony and thereby populating another place.
Right.
Where they too will grow and learn that there are elders and ancestors, were ancient wise creatures, and then come to planet, and then come to Earth in order to find us, to understand where they came from, what their home was, and then they'll see the remnants of a lost colony.
Yeah, they might just come back to ruins.
Pure ruins.
Yeah.
That's where the Egyptians went.
Yeah.
Yeah.
Mm-hmm. Yeah, the Egyptians went to space. And
Aztecs?
Yeah.
Yep.
Okay, yeah. That explains all the pyramids.
That explains the pyramids and the spacecrafts that they made before.
Oh, yeah.
Yes.
Yeah, the Sphinx was a spacecraft.
It was a spacecraft.
Okay.
I mean, it still is.
Yeah. We can't figure out how to.
We can't figure out how to operate it.
Yeah.
So, would you, Brittany, if we had a group of 100 coloners and we had a ship and you could decide whether we're going to the next planet in order to start and inhabit it, would we go?
I would go as long as the colonists weren't assholes.
You just go through and interrogate all of them. Are you an asshole?
No, man, no, I'm good. But it's true. Like, you don't want these awful people to go with you to colonize a planet. You don't want somebody who is like, all right, what's in it for me? Are they going to build, this corporation and, only put profits over people, over the good of the planet itself that we're going to? So, yeah, I would do it as long as I wasn't with assholes.
Nice.
Yeah.
So we have to develop some type of society to where we can live together in harmony and actually grow and cultivate. Because imagine going to another continent and trying to colonize it, right?
Right.
Now imagine an entirely new planet with entirely new problems that are unforeseen and completely unpredictable.
Right.
Who do we even need? Scientists, obviously.
Obviously.
Medical professionals. That'll be tantamount to survival.
Right. We also probably would need engineers.
Engineers, yes. Some civil engineers. Got to build those.
As much as it pains me to say, but yes.
Engineers?
Some engineers are... Okay, I won't get into it.
Brittany, we're supposed to make fans, not shoo them away.
Engineers are great. They're real great, and they're not full of themselves, and they don't think that they're better than the hard sciences. Okay.
Okay. All right. You have it out of your system now?
Yeah, I'm good.
Okay.
Yeah.
So we put all of these people together, and we then go and hopefully just slowly spread.
Slowly. Not like a plague,
Okay.
Yeah.
Before then, though, Brittany, hopefully, especially when we do our climate change episode,
Yes.
we can talk about how we can live long enough in order to make it to a day where we might be able to see a spacecraft going to another planet.
Yeah, that would be great to be able to see a spacecraft that could actually reach near light speed and head off to Proxima Centauri B.
One-way trip.
Yep.
Got a one-way ticket.
Yep. It could be two-way. I mean, 4.2 years. That's not that bad.
8 years?
Yeah.
8 years of travel? I can barely make it an hour in my car without wiggling my butt.
That is true. I don't like long rides.
It's true. So, I guess we'll find out.
Yeah.
And hopefully, through the efforts of everyone, including the corporations, but not like they listen to us,
No.
we can potentially reduce our harmful effects to the planet and save it just a little bit longer.
Just a little bit longer. Once we're off of here, sure, destroy yourselves, but...
Right.
Yeah.
Okay, well, I think we took a good look at planets and what's out there.
Yeah, I think we did too.
And of course, we will always put our references up for you guys to go and check out more. Brittany, I'll make her put up all of the links to the methods if you want to get more into the math of it.
Yeah.
And perhaps we can put pictures of whatever else.
We could put pictures. People like pictures.
People love pictures.
Pictures and videos. We'll do that. Don't worry.
And of course, if you have any questions, please email us or contact us however you would like. Tell us if we should or should not travel to another planet and infect it slowly and become one with the universe.
Yeah, so you can actually contact us either through email. Our email is prtcast@gmail.com. You can find us on Facebook under Periodic Roundtable. And you can also find us on Instagram or Twitter under PRTcast.
Thank you guys, and tune in next week for...
So next week, we will be talking about the science of addiction.
Ooh, I'm already addicted to the show.
Oh, yeah.
Ho, ho, ho.
Yeah.
They're not addicted.
They're
to
not
the show.
addicted.
Okay. All right.
We'll make them addicted.
Okay, the science of addiction and how to be addicting.
Yes.
Yes. All right. Thank you guys, and we'll see you next week.
See you next week.